that does relate to what you're going to have on the test on Friday. You're going to be doing problems that relate to proof by induction that have appeared on recent HL exams. But I did say that I would let you work in groups on that one, so you can work in like groups of 2 or 3. That's only specific to math induction, so there's nothing on tomorrow's problem set that relates to like the later style of proof things, like proof by contradiction, contrapositive. That's not on tomorrow's IB problem set. But Wednesday, I will give you, I think Wednesday is a rocket refresh day anyway. It just happens to line up. I love when the school says this is the time when you should rocket refresh, whether it makes sense or not, but it does actually line up with our test this Friday. So Wednesday I have a clean sheet of practice review problems of all the different kinds of proof stuff we've been talking about. So there's some induction on there, but there's also the indirect style proofs, contrapositive and proof by contradiction. There's some casework, there's some using counterexamples to show something is false, like all the stuff we've talked about that would be important for the test. I have like a set of new problems to practice that I'll give you on Wednesday. We can work on during Rocket Refresh. We will be able to talk about that stuff on Thursday, and then the test will be Friday. So that's sort of the end of this week, and then we'll be done with the proofs unit. Okay? But I want to make sure we're starting in the right place here. Is this where we got to? Did we do? I know that we did the limit stuff, right?
Yeah.
For this limit. Did we do anything with de Moivre's? We didn't do any of this yet. Okay, so let's start here then. Okay. Okay. So this part is the part that's worth the most points on all this. This is 8 of the 28 or 29 marks, whatever this was. So there's a lot of points to get here. There's not actually a lot that you need to do here, and it's probably the part that you would be the most familiar with because it's tied to stuff we did in the complex numbers unit with de Moivre's here. But it does tell you how to get started with this, right? It says, working in modulus argument form, find n solutions to this equation. So it doesn't even mention de Moivre's, but it does get you on the right track because you can't do de Moivre's unless you're in polar form, which is what modulus argument is. So first we have to rewrite this equation as with the modulus argument form of 1. So what is that? If I use r and theta instead of x and y, how do I write just the number 1? 1 says 0. Right. Okay, and if that's what z to the n is, and we want z, we want to get the n solutions to this equation, what power are we going to raise both sides of this to? 1 over n. So that's where de Moivre's comes, right? It's 1 cis 0 to the 1 over n power, and we're going to get multiple answers for this. Now, how many answers you get depends on n, right? There's going to be n different answers. They did put a restriction on n. Do you notice?
It has to be
Greater than or equal to 5. So the fewest number of solutions we could get here is 5, but the bigger n is, the more solutions there would be. Now, it just says find the n solutions. So we're not going to write every single one, but we can write out what the solutions start to look like. So the first solution, if we just apply de Moivre's to this, it's r to the n, 1 to any power is still 1. And then you're supposed to multiply the power by the original argument to get the new argument. But since the original argument is 0, whatever this power is, the first argument you're going to get in the answers is also 0, right? So 1 says 0 is your first answer. And that makes sense because what you're trying to figure out is what are the nth roots of the number 1. And no matter what n is, the number 1 is always going to be one of those answers, right? So that's what we have here. Okay, now there's the whole idea of having multiple answers. So by the way, out of these 8 points, this is probably at least 4 of the 8 just to get this, right? You're probably going to get 2 for converting 1 to modulus argument form correctly, and you're going to get at least 2 for applying de Moivre's theorem, like showing what the new r and the first new theta would be. So that's already probably 4 of the 8 points, okay? Then the next thing to show is what happens with the rest of the roots. So remember, they're all evenly spaced around the circle. They're all going to have the same r, so this 1 is never going to change. But the argument will, right? So if the first argument was 0, how are we going to figure out what the next argument is? It's going to have to be in terms of n, right? But what can I write down for the second argument? How far around the circle should we go if we've got to evenly space them? Yeah?
2 pi over n.
2 pi over n, right? That's how much space you've got, 2 pi radians around the whole circle, and you're going to space n roots around that. So you've got 2 pi over n in between each consecutive pair. So if the first one's at 0, the next one's going to be at 2 pi over n, right? What would the next one be? 1 cis, what follows that one? James?
4 pi over n.
4 pi over n. Okay, and then this is going to continue, right? So then after this you can do dot dot dot, but it doesn't go to infinity, right? There is a last one. We should write that down. Like, where is this going to stop? The last one will be 1 cis. How are we going to write what the last one is? Behind, what you got?
2 pi over, wait, sorry. It's like 2 pi k over n, but k I guess is like n minus 1.
N minus 1. Okay, so you're going to have 2 pi over n, and then you're going to multiply this by n minus 1?
Yeah.
Okay. Does that make sense to people? Like, you got to keep track of like how many 2 pi over n's are you adding, right? This is where we added one of them. This is 2 pi over n's. The next one would be 3 pi over n's. What's the last one? Well, if we add n 2 pi over n's, where are we? What is n times 2 pi over n? That's 2 pi. But 2 pi is in the same place as something we've already said. 0, right? So if we add n 2 pi over n's, that's the first time we repeat. We'd be back to this one. So this has to be 1 before that, right? So you're going to add 2 pi over n minus 1 times. That's the last one before they start to repeat. Does that make sense? There's another way to think of this if you're confused by where we're getting to n minus 1. And this goes to, they're going to have you show this on a diagram in a second. But if we're on the unit circle here, okay, and here's our first one at 1, 0, and then here's our next one at this angle here, we added 2 pi over n. And then you're going to evenly space these around, depending on how many there are, right? Where this exactly is a little fuzzy right now, but you're going to be adding them. But if they're evenly spaced, the last one before you get back to the place you started has to be the same distance away around the circle that this was, right? So if we go up 2 pi over n here, if we go back here, you could think of this as we're subtracting 2 pi over n. So we could also write that last one as 1 cis negative 2 pi over n. Does that make sense? That's equivalent. But if you think of it as this was 2 pi, so all the way around would be 2 pi, but we want to go back 2 pi over n. We're going to subtract 2 pi over n from 2 pi. And if you write this as one fraction, it's 2 pi n minus 2 pi all over n. And if you take out the 2 pi, it's 2 pi times n minus 1 over n. That's the way behind it. Does that make sense? Okay, so any way you can get to that last one, but this would definitely be at least one of those 8 points too, like showing how you get modulus argument form, applying to mobs correctly, showing how the subsequent roots like have the same r, and making clear that you're adding the same amount each time. But then there's going to be at least one point down here for showing like you're not going to infinity, so you got to be clear about where did you stop. Okay. And does it make sense? I didn't number these, like these are different z's. So I could say this is like z1, z2, z3 up to zn. I'm actually going to start on 0 here because it's going to go nicer with what they say when they start talking about the p's. There's like p0, p1, and so on. So think of this as like how many 2 pi over n's have we added? In the beginning you didn't add any yet, so that's like your z0. Then we added 1 2 pi over n here, we added 2 here, and then this last one would be z what? n minus 1. Right, because we added n minus 1 2 pi over n's. And if you go from 0 up to n minus 1, that's the same as going from 1 to n. So there are n different values here. Does that make sense? All right, any questions on the setup for the roots? Okay, then I think the next part is setting up the diagram. Yeah, now this is sort of this is funny, this is like the opposite scenario point-wise from the first one. The one before this was 8 marks, right? And you don't really have to write all that much to get all those 8 marks. Like the first line is 2 of them. By the third line, you've probably got 4 of the 8 already. So it's not like you have to do a ton of work to get the 8 points. Now here, they're asking you to do this diagram. They have a lot going on in the diagram, but the whole diagram is only worth 1 point. So this is kind of like an all or nothing point. There are a few things you'd have to get right in this diagram to earn that point. Okay, it says represent these on an Argand diagram. Let the positions be noted by P0, P1, P2. So the position, these are just points, right? But each point is corresponding to one of the roots. So P0 is like our Z0 value. That was right here. That has to be on the x-axis because the argument is 0, right? Now, where you put P1, P1 goes with, the number was 1 cis 2 pi over n, right? So obviously where it falls is a function of what the n value is. Do I have to put P1 in quadrant 1? Can you think about it? Remember, we do have restrictions on n. Does P1 have to go in quadrant 1? What do you think? Yes? No? How many say it's not required that P1 goes in quadrant 1? How many say it is? Okay, we got more people that say it is. Somebody who says it is, make the case that it has to be. Why can't it be anywhere but quadrant 1? James?
Because it is at the very least 2 pi over 5, and then
right?
quadrant 1, or it's going to be like closer to 0.
Good. Okay, 2 pi over 4 would be what? What's 2 pi over 4 the same as? And where are you at pi over 2? The end of quadrant 1, right? But we're not allowing n to be anything smaller than 5, right? So if 2 pi over 4 is here, 2 pi over 5 is going to be before you get to the end of the quadrant. And then the bigger n gets, the closer to 0 you are, right? So you do have to put P1 somewhere in quadrant 1. That would be one thing that they'd be checking. Notice they say, show the positions of P0, P1, P2, and Pn minus 1. Only those 4 do you have to show. There's n of them, and n is at least 5, so you're not showing them all. But you have to show enough that you understand like how this diagram would look. So P0 has to be on the x-axis, no choice. P1 has to be in quadrant 1, but you can be arbitrary about where you put it in quadrant 1. Let's just say I put it here. Okay? But now that you've committed to that for P1, do you see that you're not exactly free to just plop P2 and Pn minus 1 anywhere you want? What has to be true? What are they going to look for to make sure that you have P2 and Pn minus 1 correct based on where you put P1? That's what they're going to look at. They're going to look at, is this one on the x-axis? Then they're going to look, did you put P1 in quadrant 1? Then based on where you put quadrant P1, they're going to see if you've placed P2 and Pn minus 1 correctly. What do we think? What needs to be true here to get credit for this diagram? Like the way I drew this, should P2, what quadrant should P2 be in? Quadrant 2? Okay. Do you see that if I put P1 here, which would be allowed, now where would P2 have to be? Still quadrant 1. Are you seeing what I'm doing here? What has to be true about where P2 goes based on where I put P1? What should you be thinking as you decide where's the location for it? No. P2 will be further along the circle, for sure, right? But you can't just say that. It's not enough to just say it's somewhere past P1. It is, but we have to be a little more specific than that. Bihan?
It has to be equidistant, like PO and P1, the same distance as P1.
Right. Does that make sense? The whole thing is they're evenly spaced. So once you've committed to this, that's how much space there is. So if I'm going to put P1 here, then P2 should be like about here, roughly. No one's getting out their like measuring device to say, oh, you're a little bit off, okay? But if you put P1 here, and then you put P2 here, they're going to be like, no, okay? You have to have like a believable attempt that you have them equally spaced, okay? Now, they only said P0, P1, P2, and Pn minus 1. Where do I put Pn minus 1? Is Pn minus, let me ask you this way, is Pn minus 1's quadrant fixed? We said P1 has to be in quadrant 1, right? Does Pn minus 1 have to be in a certain place? Where? Quadrant, it's not 3. It's 4, yeah. It's got to be here. Because the same thing, right? However far you went here, you're going the other way, but you're going to go the same distance. So if you didn't get all the way to the end of quadrant 1 here, you're not getting to the end of quadrant 4 here, right? In fact, does this make sense? Pn minus 1 should be vertically reflected from wherever P1 is, right? So if this was my P1, then Pn minus 1 would be right there. Does that make sense? Because if you go like up clockwise a certain angle, and then you go counterclockwise the same angle, you're going to end up with the reflection of that point over the x-axis. Try away. Yeah, did you do a pass around? Okay, are we good on all that? So that is kind of a lot to put in, like a lot of things they're looking for. And if you mess any of those up, you're not getting that 1 point, which is annoying, but on the other hand, it's only 1 point. Right? Is everybody okay with all that? Any questions? Okay. All right, so now the next piece says, show that the length of the segment P0, P1 comes out to that expression, 2 times the sine of pi over n. Okay, so they just want the length of that segment, right, from P0 to P1. So does anybody have an idea of how to go about, they're giving you the result here, and this is another very interesting way they asked this. They could have said, find the length of P0, P1, and just had you come up with that expression. Find it in terms of n, and that's what they would want. They didn't do that. They told you what this was going to be. And the reason they told you what it was going to be, and they're just giving you points for showing the work to get there, is because you really need this expression to be correct to get a bunch of the points that follow this. So instead of having to deal with like a nightmare of follow-through points, which they do sometimes do, but here, like if they had to take every possible answer they got from this and apply that to all these questions later where you really need this to get the right answer, it's a lot harder for them to evaluate how many points did you get on the subsequent parts. So that's why they wrote it this way, okay? It's also important to know that if you get stuck on this part and you can't figure out how to do this, this is the thing that's important for earning the points later. So even if you couldn't figure out how to show this length, if you know that the length is supposed to be that, that's all you need going forward. Like you're not hindered from getting any of those other points if you can't figure out how to earn these 4. Okay, so keep that in mind. Don't get too bogged down with time. Like you know that it's about a minute per mark. You guys will actually get a little bit more than that because for you this year in paper 3 they added an extra 15 minutes to your time. So before this, paper 3 was an hour and you had 55 points to do it in an hour. Now you guys have an hour and 15, 75 minutes to do 55 points worth of stuff. So you get a little bit more than a minute per point, but be aware that like if something is 4 points, you don't want to be spending 10 minutes on that, right? Because you probably want those other minutes somewhere else. All right, any thoughts about how to get that 2 sine pi over n for the distance? They want the distance of this segment. There's a couple different ways to do this. I thought of 2 different ways, and then when I looked at the mark scheme from IB, they did it a different way from what I did. I was actually kind of annoyed. I think their way is a little better, but I didn't think of it. But all of them will get you to this. Okay? But I'm interested to hear what you guys thought. What is a way we could get the length of that segment? Francis?
You know that the radius, so the distance from the origin to P1 and P0 both 0. So you can say that,
You mean 1?
Yeah, both 1.
Okay.
So you can say sine pi over n is equal to P. Yeah, I don't remember what I did.
Okay, that's actually, I think you're on the right track to the way that IB did it, that I didn't think of, but you're missing one piece there.
I said it equals to P, to the segment P0, P1 over 2. I don't remember why I did that.
Okay, yeah. Did anyone else do something like what Francis is describing here? Behind, did you do it that way?
Yeah, I guess Francis probably bisected that triangle.
Yes. That's where I think you're going. Like you're bisecting this triangle
Yes,
because it's isosceles, right? Since you were starting to say that, since both of these are 1, it's an isosceles triangle. If you bisect that angle, you might remember this from geometry, that's going to be a right angle. And those 2 triangles are congruent, right? And that means the length we're looking for here, if I call this t, each of these would be t, so the whole thing would be 2t. But I could find the length of that because I have a right triangle here. Now, what was the original angle before I bisected it? That's after you bisect it. 2 pi over n, but if you bisect it, each one of these small angles is pi over n. Does that make sense? Okay? And one thing, like I was thinking, I never thought of doing that. But if you see that the final answer is in terms of pi over n, and you know that this angle you're working with is 2 pi over n, that might give you an idea to bisect it. It didn't to me, but it probably did to some of you, and that's the way IB's mark scheme is set up. So if we just take that triangle out, this is t, this is the right angle, this is pi over n, and we know the hypotenuse is 1, and I'm looking for t, so I know sine of pi over n is t over 1. So that means sine of pi over n is t, but the length I want is double that. So if this is equal to t, 2t is just 2 times this. Okay? So if you did that, that's enough work to get those 4 points. Okay? That is, I think, the easiest way. It's not the way I thought of. And if you didn't think of bisecting the triangle, is there anything else we could do? Like, you are not actually stuck here. This answer doesn't depend on you thinking of doing it that way. Can you think of anything else? Think about the fact that they're asking for the distance between 2 points. Don't we know what the coordinates of those points are? And if you have the coordinates of the points, what's the normal way you find the distance between them? Distance formula, right? Okay, so where is P0? What are the coordinates of that point? 1, 0. Okay, now P1, what we know about P1 is it's on the unit circle, and we know the angle you use to get there is 2 pi over n. How do we represent the coordinates of any point on the unit circle? Cosine sine. So P1 should be at cosine 2 pi over n sine 2 pi over n. Does that make sense? So now we're going to use distance formula to get the distance between those 2 points. Okay, this is the way I did it. Okay, distance is square root of a bunch of stuff. What do we put under the square root? Start with, subtract the x's. So 1 minus cosine 2 pi over n. It's those, the difference in the x's squared plus, what's the other piece? Difference in the y's. Now the y's are 0 minus sine 2 pi over n. It's just negative sine 2 pi over n. It doesn't even matter about the negative because I'm going to square. Are we okay there? Okay, so this is a valid expression for the distance, but we have to do some work on this because we have to get to that. So what's obvious to do next here? Expand. So I'm going to get under the root still 1 minus 2 times the cosine of 2 pi over n, that's the middle term, plus cosine squared 2 pi over n, and then this is going to be sine squared of 2 pi over n. Everybody okay with that? Okay, now what can I do? This is like your pre-cal selves coming back here. Right? What's the next thing to do? What's this? 1. And we already had another 1. So now we've got root 2 minus 2 cosine 2 pi over n. Okay, still not that. Okay, but it does help that you know what you're trying to get to. You know what you should be doing. The problem here is the angle we're dealing with is 2 pi over n. The angle we're supposed to be dealing with is pi over n. So what does that suggest about what we could do here to get that? Well, we can factor out 2, but that's not going to help with the angle. Yeah, we need an identity for cosine. We have cosine of twice the angle we're looking for. So this sounds like we're going to use the... Yeah, what's the name for this identity? Like when you are dealing with an angle that's twice as much as the other? Double angle. This is double angle for cosine. Now this is in your packet. You don't have to remember it. But if you look in your packet, you're going to see the double angle for cosine is the one that has 3 different forms. One has both sine and cosine in it. One has only sine. One has only cosine. If those are your 3 choices, knowing what you're trying to end with, what do you think is the more efficient choice to use? The sine one. Okay? So you can look this up in the packet. I will do what I think Shreyan said too also. I'm going to take out the 2, and then it's 1 minus, and in place of cosine of this angle, I'm going to do the double angle formula that only uses sine, which is 1 minus 2 sine squared of the angle that's only half as big as this, pi over n. Are we good there? Okay, I maybe overcomplicated it with the factoring out the 2. I don't know. We got a 2 here, then we got a -2. Those are going to cancel. And then I'm going to get, there's 2 negatives here and a 2. Do you see what I'm going to end up with here? What's going to be the end result under the root? So I have a 4 sine squared pi over n. And if I take the square root of that, the 4 goes to 2 and the sine squared goes to sine. And I get the thing I'm looking for, 2 sine pi over n. Okay? Okay? So you can get there from distance formula. That's what I did. I will say I messed it up too when I did it. I did this, and then when I did my double angle, I forgot to go from 2 pi over n to pi over n, so I still had a 2 pi over n there. Like, I messed it up. But if you do it correctly, you get the thing that you're looking for. Okay? But even if you got lost here and you didn't see how to get to that, like, don't spend a long time on that, right? That's 4 points. If you've written some stuff down here, you're probably getting some of the 4. But the key is having that value, not this. You're not going to need your work in the later parts. You're going to need that result in the later parts. Okay? Does that make sense? Any other questions on part E? All right, part F is really quick. Okay? Hence, meaning, when IB says hence, using what we just did before, write down the total length of the perimeter of the regular n-sided polygon that you get by connecting P0, P1, P2 all the way around, ending at Pn minus 1, and then reconnecting to P0. So if you go back to our picture here, right? Here's the beginning of the polygon, P0 to P1 to P2. These are going to keep connecting. You're eventually going to get to Pn minus 1, and then you're going to reconnect. So there is a polygon being formed there, right? And it wants to know what the perimeter of that polygon is, or what an expression for the perimeter is. But it told you it's a regular polygon, meaning, what's the term regular with polygon mean? All angles are the same, and more importantly, what else is the same for here? All the sides are the same. So if we just found the length of one of the sides, or actually they told us what it was, we just had to figure out why it was that. And now we want the perimeter of the whole thing. What do we have to do to our answer from the previous part? Multiply by n. That's it. You get a point for putting an n next to the answer that they gave you from part E. Okay? So the perimeter is going to be n times 2 sine pi over n. Writing that down is 1 point. Okay? If you want to make it look a little nicer, it's 2n sine pi over n. But making it look nicer, not required for the 1 point. Okay? Does that make sense? All right. Then they're going to ask you, following that, using part B. Now, part B was the limit, that sandwich theorem piece, right? The limit as alpha goes to 0 of alpha over sine alpha was 1. And remember, you didn't have to figure out this limit. They told you this limit was 1, right? So now they're saying, using part B, find the limit of the perimeter. So find the limit of this as n goes to infinity. Now, that is not super obvious. Okay? What they want you to find is the limit as n goes to infinity of the thing we just wrote down, which was 2n sine pi over n. So they want you to find that limit using that. It does say using part B, so it's only 2 marks here. This time they did ask you to find the limit, so one of the points is actually for the answer. But the other point, and it's probably tied to the answer point, is you've got to show how you're going to make use of that limit in the course of finding this one. So you're going to get 1 point for showing how you made the connection between that and what you tried to find out, and then the other point is for getting the right result from doing that. If you try to get the limit another way and you're not using part B, you're probably not getting either of the points there because they had in the directions using part B. Okay? All right, any ideas? It's not obvious, right? Like, we don't have this expression in there. This is limit as alpha goes to 0. This is limit as n goes to infinity. What you want is to try to establish a relationship between alpha here and n here, right? Can you see what a possible connection between alpha and n could be? Look at what look at where, compare the two sign expressions that you have, right? Here we're taking the sign of alpha, here we're taking the sign of pi over n, okay? So that suggests a possible relationship between alpha and n. Do you see it? What could we let alpha represent so that this limit gets used in finding that one? Vihan. How about pi over n? Because that's what we're taking the sign of, right? If alpha is pi over n, first of all, if alpha is pi over n and n goes to infinity, what happens to alpha? If alpha is pi over n and n is going to infinity, what is the effect on alpha? Alpha is going to go towards 0, which is what we have here, right? So can we rewrite this limit in terms of alpha? Okay. Everywhere we see an n here, we want to put the expression in terms of alpha. Now, here I have alpha is pi over n, but do you get that that would also mean that n would be what? If we want to write it the other way, what is n in terms of alpha? Pi over alpha, yeah. Okay, so here I have the 2, and then in place of n I can write pi over alpha. And then I'm taking the sign of pi over n, but we already said pi over n is alpha. Okay, so does it make sense? This limit in terms of alpha is equivalent to that limit in terms of n. Okay? Now, the 2 and the pi here, how do I treat those? If I'm taking the limit as alpha goes to 0, or alpha goes to 0, the 2 and the pi are treated like, as far as limits go, what can we do with those? Right, so they can just come outside the limit, right? The 2 and the pi are just going to stay there. So it's going to be 2 pi times the limit as alpha goes to 0. What's left here? Sine alpha over alpha. Okay? Now that's the reciprocal of what we had here. Here in part B you said the limit of alpha over sine alpha as alpha goes to 0 is 1. So this should go to the reciprocal of that result, right? But since that result is 1, what's the reciprocal of 1? Still 1. So that limit's going to go to 1 also. So the final answer here is 2 pi that you pulled out times the 1, which means we're going to get 2 pi as the answer. Does that make sense? All right, now I want to show you something that wasn't in the question here that helps visualize what we just did here, and it will also show you why what they're going to next makes sense. Okay? I did not make this, I just found it in GeoGebra, but this is a description or a picture of the nth roots of 1 where we can slide the n value. So this is showing for the first case that they're telling us to look at, right? This is what the 5 roots would look like if we had just 5 roots. These are the 5th roots, okay? You can slide this back and we can see, like, if we go all the way back, like the 2 roots, if we had the 2 square roots of 1 are 1 and negative 1, right? Cube roots, we would have 3, 1 would still be one of them, these other 2 complex numbers, right? And so on. But here's the first one they had us look at. And what they're saying, and do you see, like, these points on the pentagon here are all on the unit circle, right? If I could have tailored this a little bit more, I wish they would have drawn the circle here. But imagine all these points are on the circle. These green lines are all radii, right? So if I increase the number of roots, I get a larger polygon with more points along the circle. But do you see what's happening as I increase the number of roots here? The perimeter of this polygon is starting to look more and more. I can stretch it out more. I think this goes up to like 20. Right? What does that resemble? What circle? The unit circle, right? So the more points I have here, the closer this polygon is to resembling the unit circle. What is the perimeter of the unit circle? 2 pi. 2 pi times r. R is 1, right? So the more points you have here to make a bigger sided polygon, the closer that polygon is to the unit circle, so its perimeter is going to get closer to the circumference of the unit circle, which is why we got the 2 pi for what we just did. Okay? Do you see what they're going to ask you next is the same idea with area? The more sides we have in the polygon, the closer this looks to the unit circle, so the area of this polygon should get closer to the area of the unit circle. What's the area of the unit circle? Pi r squared, but r for the unit circle is 1, so the area would just be pi. That's what they're heading to in the last part. Okay? All right, so to get to that last result, they first want you to give an expression for the total area of the polygon. Can you see how we would, even from this picture, if we were focused on one triangle, and last time we were just trying to get the length of that side, now we're trying to get the area of the triangle. If we just focus on one triangle here, right? What are these two sides? One each. And what's that angle? Remember how many radians are between consecutive points? 2 pi over n. Okay? So the area of one of these triangles, what's the appropriate area triangle formula to use here? I know two sides and I know the angle between. This is in the packet also, but you guys probably remember this from pre-calc before. How do you get the area of a triangle if you know two sides and the angle between? Behind.
1/2 any sides.
So here that's 1/2, the A and the B are both 1, and the angle is 2 pi over n. So it would just be 1/2 sine 2 pi over n. Right, that's one triangle. Now to get the whole polygon, what do I have to do to that answer? What is this in relation to the whole thing? Go back to this. Right? We would get the area of one of these, but the polygon is made up of how many of them? N, and they're all the same size, right? So what do we have to do? Multiply that by n. So the area of the whole polygon would be n over 2 sine 2 pi over n. Does that make sense? That's those points. Now they're going to ask the same thing with area that they asked for perimeter. What is this heading towards as we go to infinity? We know from the picture that the answer should be what? Pi. It should go to pi. But they want you to use that same limit to show again that this limit's going to come out to pi. So we're not using the geometry argument to get the answer. We're using the calculus argument. So I want to take the limit as n goes to infinity of n over 2 sine 2 pi over n. But I'm going to use my same limit from part B. Limit as alpha goes to 0, alpha over sine alpha is 1. Last time we made the substitution that alpha was pi over n. What would be an appropriate substitution this time? Let alpha be, why did we let alpha be pi over n last time? Why did we do that? Do you remember? What made me do this? James?
Put one limit into the other.
Right, and why did I choose alpha to be pi over n specifically? Like, how did that help here? Anand?
There's like a seemingly there's like a relationship, like it's like what is that alpha over sine alpha.
Right, and I'm taking the sine of alpha here, right? And in this one I was taking the sine of pi over n.
Right.
So that's why I want to put the alpha where the pi over n is. But in this one I'm not taking the sine of pi over n. Right? I'm taking the sine of 2 pi over n. So let alpha be 2 pi over n. Okay, if we do that, is it still true that as n goes to infinity, alpha is going to go to 0? Yep. So this limit as n goes to infinity converts to limit as alpha goes to 0, right? And then the n's get replaced with 2 pi over alpha. So this is 2 pi over alpha over 2. Those 2's are going to cancel, right? And then it's the sine of 2 pi over n is our alpha. So the 2's already canceled. The pi is a constant. It can come out. So this is pi times the limit, alpha goes to 0, of what's left here is just sine alpha over alpha. And same thing, since that limit was 1, the reciprocal of this is going to go to the reciprocal of 1, which is still 1. So this is pi times 1, and we get the answer we said we should get, pi. Okay? I want you to appreciate a couple things here. Mainly, even though overall, like you could say, like there's a bunch of places where it's like tricky to get full credit in a certain part, but you see that there's a lot of clues in parts that are not dependent on you getting that answer correct to be able to earn points later on. Okay? So it's important not to give up on a problem. If you get stuck on like part E or wherever that one was, and there's all these other parts later, they're usually giving you the information you need to be able to do things later, so that if you get stuck on a problem, you're not doomed to just like concede all the rest of the points. That's not usually how these are set up. Okay? They're trying to help you earn as many points as you can. But there is some strategy to like do this strategically. Don't get bogged down in any one particular part. Okay? And over the course of the year, we'll do more practice with these, so you'll get a greater appreciation of when I say I think this one skews to the harder side. You'll see some others that are not as difficult. The other thing to keep in mind is this is the equivalent of half of a paper 3 test for you, right? You get 2 of these to do in an hour and 15 minutes. So this would be like 35-ish minutes that you'd spend on this. The other problem on your test will most likely not be at all related to this one. Like the 2 problems will be on 2 totally different areas. So if this one is on like complex numbers and calculus stuff, the other one is likely to have nothing to do with that. It might be probability, might be vectors, might be like pre-cal function stuff, but it's probably on a totally different area. When you read the 2 questions, remember you get the reading time with IB exams, 5 minutes before you can like work, where you can like see what the questions are. You'll read the 2 questions and decide which one you think you can do better on first, and then watch your time. Spend 30, 35 minutes, not more than 40 minutes, even if you don't get all the way through that. Because if you're still working on this problem more than halfway into the test, you're probably working on stuff that's the hardest points to get at that point. And if you switch over to the other problem, there's going to be a bunch of easy points to get there too. So you want to make sure you earn all the easy points before you spend your time working on the harder stuff. Okay? All right, that's good. Remember, this does not impact you for the test this Friday at all. You don't have to be reviewing this stuff. But tomorrow, induction proofs as the IB problem set, and then Wednesday I'll give you practice problems that relate to Friday's test. Okay?